Okay, let's unpack this. Imagine, for a moment, that our planet isn't just, well, a solitary rock hurtling through space. What if it's intricately intertwined, maybe even physically interpenetrated, by a completely different unseen version of itself? One made not of, ordinary matter, but of that mysterious dark matter.
Yeah, it really does sound like something straight out of a blockbuster sci-fi movie, right?
Exactly. Well, today we're taking a deep dive into precisely that fascinating concept. Our mission really is to explore these theorized dark plasmaspheres, the ones that are believed to interpenetrate our ordinary matter, Earth. And we're drawing our insights from this really groundbreaking paper, Earth's Dark Plasmasphere Structure and Dynamics by J. Alfred, published July 20, 2025. It's quite a read. Mind-expanding, really.
hmm What's genuinely fascinating about this paper, I think, is that we're moving beyond just the abstract idea of dark matter, as just some invisible stuff out there. Alfred presents, a concrete model, proposing actual structured objects, celestial objects, really.
Right, not just fuzzy clouds.
Exactly. These aren't just theoretical blobs. They come complete with their own uh, intricate physics and dynamics operating right here, around us, within us. So our goal in this deep dive is to really try and grasp what these enigmatic structures are made of, how they behave, and maybe most importantly, what the implications are for our understanding of reality itself, and maybe even life.
Okay, so let's start right at the beginning, the foundational question.
Yeah,
What exactly is a dark plasmasphere? Because, when you hear plasmasphere, you might think of Earth's magnetosphere, that protective bubble we know about.
sure. The ordinary one.
Right. But Alfred's paper is talking about something profoundly different, though, maybe conceptually similar in some ways. He defines it as a theorized celestial object, yeah, but one that's not just orbiting us, it's actually nested within our ordinary Earth, interpenetrating it.
That's the key part, the interpenetration.
And here's where it gets really interesting. Its composition. He calls it dark non-thermal, or cold, complex, or dusty plasma. Now, that term plasma crystal, it sounds like a contradiction, doesn't it? Crystal means solid, ordered. Plasma, usually not so ordered.
Usually thought of as a hot gas, yeah.
But the paper highlights that these dark spheres actually display properties of plasma crystals, meaning despite being a fluid, their particles can, under certain conditions, arrange themselves into this incredibly ordered, almost lattice-like structure,
Wow.
which implies, a surprising level of internal stability, organization. Within these dark plasmaspheres, it's sort of familiar concepts applied to this totally unseen realm.
That's precisely right. And the whole model, everything rests on this one critical assumption, the existence of asymmetric dark matter around Earth.
Asymmetric, okay.
Yeah, this is key. Because if dark matter were symmetric, right, you'd expect roughly equal amounts of dark matter and dark antimatter.
And they just annihilate each other.
Exactly. You'd see all this annihilation activity, release of energy. But with asymmetric dark matter, that annihilation, it's largely absent. Instead, what you get is this continuous process, capture and accumulation of dark matter particles around Earth. And the author, J. Alfred, he's actually been working on this for a while,
Yeah.
since 2005, proposing that this self-interacting dark matter around Earth isn't just some diffuse cloud. It's actually a highly ionized, low-density dark plasma.
Right. So, okay, the big question then is, why plasma? Why does this dark matter, under these specific conditions, form a plasma state? We're so used to thinking solid, liquid, gas, right? But Alfred's paper lays out some really compelling reasons why dark matter here would naturally end up as plasma.
Yeah.
First off, the weak dark electric charge.
Ah, yes.
The paper estimates this charge is just astonishingly weak, like a tiny fraction, maybe down to 1/1,000,000th of the ordinary electric charge we know.
A millionth. It's
Yeah.
barely anything.
Exactly. Think about how profound that is, this inherent weakness. It's a critical factor. It means the force is simply too weak to easily bind charged dark particles together into stable atomic structures. Not like our electrons and protons, which bind really strongly.
It's like trying to build with faulty Lego bricks almost. They just don't click together properly.
Good analogy. And then compounding that weakness, you have the sheer preponderance of neutral particles in these dark sectors.
More neutral than charged.
Way more. The author estimates that neutral, or he calls them pseudo-neutral, dark matter particles actually outnumber the charged ones by about 5.5 to 1.
5.5 to 1. That's the opposite of our universe, isn't it?
Exactly the opposite.
Yeah.
Here, charged particles like protons and electrons are way more numerous than elementary neutral ones like neutrons. So this huge abundance of neutral dark particles. It acts like an invisible insulating buffer.
Okay.
It physically increases the average distance between the charged particles' fields, right?
Mhm.
Further weakening that already tiny electric force,
Got it. More space, less force.
which dramatically reduces other interactions, collisions,
Uh-huh.
making it incredibly difficult for any kind of stable dark atoms to form.
It's like the deck is stacked against atom formation from the start.
Pretty much. And adding another fascinating layer here is the idea that, according to the author's model, you generally find higher temperatures in dark sectors compared to ours.
Higher temperatures. Interesting. Why?
Well, it's consistent with some standard cosmological models, apparently, and it's sort of a necessary piece of his overall theory. And this extra thermal energy, it gives the charged dark particles more kinetic energy, more oomph.
Right, they're moving faster, more energetically.
Exactly. Which helps them overcome any potential binding energies, even the weak ones. So it actively prevents them from settling down into atoms. You
Hmm.
combine the weak charge, that neutral buffer, and these higher temperatures. You start to see why plasma isn't just an option for dark matter here. It's arguably its natural state.
Okay, that makes sense. But then there's the role of thermodynamic forces too, right?
Yeah.
Separating particles.
Yes, that's another key piece. These forces can actively separate oppositely charged particles. The paper explains that the larger dark protons, they'd naturally have a much bigger cross-section for interaction, like a bigger target.
So they collide more often.
Exactly. Higher collision rates compared to the smaller, negatively charged dark electrons. And this difference in size and collision rate means the more massive dark protons cool down much faster.
Ah, okay, so they lose energy quicker.
Right. The intriguing result, you get cold, dark protons and warm, dark electrons.
Cold and warm. That's a significant temperature difference within the same plasma.
Huge difference, which means their velocities are also dramatically different.
Mhm.
And this velocity difference tends to push them apart, creating what's known as a non-thermal or cold plasma.
Non-thermal,
Uh.
because the particles aren't all at the same temperature, the same energy level.
Precisely. In this kind of plasma, particles of different charges have very different kinetic energies, different speeds. Makes it much easier for them to avoid or break any bonds trying to form dark atoms.
It's like trying to make something stick together when one part is sluggish and the other's just zipping around chaotically.
Yeah, good way to put it. And if all that wasn't enough to point towards plasma, you also have the much lower density.
Lower than ordinary matter.
Orders of magnitude lower in terms of particle concentration around Earth. And that means much greater distances between particles.
Right.
So when particles are far apart, what dominates their interactions? It's mostly electrostatic forces, Coulomb interactions.
The long-range electrical forces, yeah. Not direct bumps.
Exactly. And that emphasis on long-range electrostatic forces rather than frequent physical collisions, that's a classic characteristic of plasma.
Okay, so weak charge, lots of neutrals, higher temps, different cooling rates, low density. It's all pointing to plasma. What about particle movement?
Ah, yes, good point. The dark matter particles are also theorized to move much more slowly than their ordinary matter counterparts. Now, combine that slow speed with the low density, and you get a big reduction in how often charged particles directly collide.
Slower movement reducing collisions. That seems a bit counterintuitive at first glance. Wouldn't slower mean more time to interact?
You'd think so, and the paper does acknowledge that. At higher densities, that slowness could actually help interactions. But here, in this very low-density dark plasma, particles moving too fast would just fly past each other anyway. So the slower velocities, combined with the low density, actually end up promoting those long-range electrostatic interactions that define plasma rather than the close contact binding needed for atoms. It's a subtle balance.
What delicate balance, yeah, okay.
And here's a really nuanced point. Even if these dark plasmaspheres aren't like 100% ionized,
Partially ionized plasma, okay.
right? Even then, the paper highlights that electrostatic forces still have an indirect effect on the non-ionized stuff through viscosity.
Viscosity, like friction within the fluid.
Kind of, think of it like this. Even if only a small percentage is ionized, those charged particles can sort of drag along the neutral particles, especially in a magnetized environment or this colloidal medium they describe.
Okay, so the charged particles influence the neutrals.
Yeah, leading to anisotropic behavior, meaning the neutrals start showing directional properties aligning with the plasma flow, and they collide frequently, exchanging momentum. So these neutral particles, which are the vast majority, remember they effectively start behaving like dust particles in a complex, or dusty plasma.
Ah, the dusty plasma concept, okay. And that has specific implications, right?
Big implications. The paper explains that in these environments, the dust particles are neutral dark matter particles. In this case, they accumulate large negative charges and get polarized. But what's really unique here, unlike ordinary plasma maybe, is that the charge on these dust grains isn't constant. It fluctuates with the local plasma potential.
The charge fluctuates. Okay. Why is that significant?
Because this fluctuation leads to totally new damping effects and even new types of plasma waves.
The waves.
Yeah, and these waves are what generate incredibly intricate, complex structures and features within the dark plasmasphere.
So it wouldn't just be a smooth blob. It'd have internal structure.
Exactly. The prediction is that Earth's dark plasmaspheres wouldn't be amorphous clouds at all. They'd show very specific signature features, much like the complex structures we see in lab plasmas and space plasmas in our ordinary universe.
Wow. Okay, so bringing all these threads together. The weak charge, the neutral buffer, the heat, the cold protons, warm electrons, low density, slow movement, the dusty plasma dynamics.
Yeah, when you add it all up, the conclusion seems pretty clear, doesn't it? The core insight is that dark matter here just can't easily form stable atoms like ours.
It seems almost inevitable it would form a plasma.
Right. It naturally organizes into plasma. It's a fundamental difference shaping this unseen world. And these dark matter particles from each dark sector interpenetrating Earth would then organize themselves into near-perfect spheres of dark plasma, driven by gravity and those weak electromagnetic interactions.
And that's the origin of the dark Earth.
That's the dark Earth, a distinct dark planet made entirely of dark matter, gravitationally bound and co-rotating with our familiar ordinary matter Earth.
The author uses that analogy, the dark dwarf,
Right.
comparing it to a brown dwarf.
Yeah, it's an intriguing comparison. Like a brown dwarf in our universe, those failed stars, too big for a planet, too small for fusion, mostly plasma.
But it's not a perfect analogy, is it?
No, and Alfred is careful to point that out. These dark Earths would have way too little mass for nuclear fusion. And unlike brown dwarfs, they wouldn't even fuse deuterium or lithium
Why not?
because of their very low density and that high ionization state. So this makes a dark plasmasphere a truly unique astrophysical object, according to the author, unlike anything else we've classified.
Right. And crucially, unlike our Earth with its rocky core, these dark Earths are highly ionized throughout, all the way through. Makes ordinary atomic or molecular matter really improbable.
But he doesn't rule out plasma chemistry, does he? Or even biology.
No. Fascinatingly, he suggests that this high-energy dark environment doesn't necessarily preclude complex plasma chemistry, or even, yes, the possibility of biological processes. A very different kind of life, obviously.
Mind-blowing. Okay, let's shift gears. From the building blocks to the sheer scale, the immense scale of these dark Earths. Because, the paper suggests they are expected to be much, much larger than ordinary planets.
Like how much larger?
The smallest dark Earth is projected to be as big as Jupiter.
Jupiter-sized. Wow, an unseen, gigantic companion right here, interpenetrating our planet.
Yeah, it definitely puts our everyday world in a new cosmic light, doesn't it?
It really does. And their formation, it's not random. It tells this grand cosmic story, a top-down process.
Top-down, how is that different from our planets?
Well, our planets formed bottom-up, right? Dust grains clumping into planetesimals, then planets.
Right.
But this self-interacting dark matter, with its weak charge, it's theorized to have contracted and cooled down from much, much larger, more primordial dark matter halos. These huge halos would have condensed first from the even bigger cosmic web structure.
Yeah.
So you start enormous, and it cools and condenses down into these dark planetary bodies.
So the big structures came first for dark matter, then the smaller ones formed within them.
Exactly. And this gives a new perspective on our own solar system's dark history. The author thinks both the dark and ordinary matter parts of our system evolved together inside this enormous initial dark matter halo.
How big was this halo?
Over 4 light years wide. Truly gigantic.
4 light years. Incredible.
Yeah. And while a lot of that original halo probably dissipated over 4.5 billion years, tidal forces, cosmic winds, etc., the cooled, broken-off dark plasmaspheres are theorized to have remained, gravitationally bound. And here's the kicker. Our ordinary visible Earth formed within the lowest energy dark halo.
Like we were born inside a dark cosmic bubble?
Pretty much. And it's not a static picture. There's ongoing interaction.
And Earth is still pulling in dark matter.
Yes. Our ordinary Earth continues to attract and accrete dark matter from various sources. Not just gravity, but maybe this conjectured fifth force and other weak interactions too. And this ongoing accretion would subtly, gradually increase Earth's mass. Over millions of years, it might even gently nudge our orbit.
Huh. Though calculating that nudge must be incredibly complex.
Oh, absolutely. You'd have to factor in accretion by all the other planets, too. It's a whole cosmic dance with these unseen partners.
So with these colossal scales, how do we even visualize these things, these huge invisible structures?
Well, the paper describes some striking structural similarities to our ordinary magnetosphere. Imagine vast, dark plasma sheaths, stretched out ovoid shapes, containing polarized regions, kind of like our Van Allen belts, but filled with oppositely charged dark particles.
Okay, so like a dark magnetosphere.
In a way, yes, and they'd contain a global dark magnetic field, too, which we'll get into. What's also interesting is that as you go to higher energy dark Earths, the ones interpenetrating further out, each one is theorized to have a larger volume.
Larger volume, why?
Because the particles inside are more energetic, so the distances between them increase. But the mass and size of the individual particles actually gets smaller.
So they're bigger but less massive overall.
Exactly. The overall rest mass of each larger, more spread out plasmasphere decreases.
You can almost picture them as these vast, invisible oceans of plasma, can't you?
That's the imagery the paper uses. These huge halos of dark plasma, subject to powerful tides, just like our oceans.
Tides from what? Earth, moon, sun?
Exactly. Gravitational interactions within the Earth-Moon-Sun system. And like Earth's atmosphere, they're in constant flux. Density, size, shape, always changing.
Why the changes?
Capture or loss of dark matter particles. Gravitational pulls. Buffeting by cosmic winds. The author paints this picture of them size shifting and shape shifting like a dancing candle flame.
A dancing candle flame? That's evocative.
Yeah, due to gravity, dark radiation from their dark suns pushes from dark solar winds, other dark matter winds. It's a truly dynamic, almost living system.
So let's dive into those internal dynamics. Are they just static spheres or?
Oh, definitely not static. There's surprising similarities to ordinary celestial bodies, like the sun, right? A rotating ball of plasma.
Yeah.
These dark Earths would likely experience differential rotation.
Meaning the equator spins faster than the poles.
Exactly, just like the sun. And this differential rotation generates a Coriolis force.
Like the one driving weather on Earth.
Precisely. And here, it could give rise to powerful plasma vortexes within the dark plasmaspheres, which also implies that day and night length wouldn't be uniform. It would vary with latitude on these dark planets.
Fascinating. And what about the length of their days overall?
Well, because they're so huge, their overall rotation is expected to be much slower than Earth's. So days far longer than 24 hours.
Longer days. Okay. Anything else about rotation?
There's even this really intriguing possibility of counter-rotation.
Some parts spinning backwards.
Potentially. Some studies of our galaxy's larger dark matter halo suggest it might be mildly counter-rotating. So the paper speculates, could some latitudes within these dark Earths do the same? Plus, the interior might rotate differently from the external surface, adds another layer of complexity.
Wow. Okay, and what about light? You mentioned dark radiation. How would they appear?
Right, their visibility, or lack thereof. Since they're plasma, the paper posits they'd spontaneously emit dark photons, dark radiation, essentially filling themselves with this diffused dark light day and night. So they're not just inert, invisible blobs.
They glow, but in a way we can't see.
Exactly. And their dark geomagnetic field, it co-rotates with them, changing size and shape too. And, like Jupiter's gas envelope, no hard surface.
So how would they look to someone who could see dark radiation?
Ah, that's where it gets really weird and cool. Their appearance wouldn't be static. It depends on how their internal plasma frequency compares to the ambient dark light from their dark sun and other stuff.
Okay.
If its internal frequency is higher than the ambient dark light, the paper suggests it would literally shine brightly, like polished metal.
Whoa.
If its frequency is lower, it becomes transparent, vanishes.
Invisible again.
And if the frequencies are exactly the same, it appears as a perfectly black ball against dark space.
So shiny, transparent, or black, depending on frequency.
Right. And since plasma frequency is tied to density, and their density is always fluctuating because of dark space weather and gravity,
They'd flicker.
they'd oscillate in brightness.
Yeah.
Becoming visible, then invisible, then maybe shiny, leading to this mesmerizing, shimmering, or scintillating appearance, a dance of dark light and shadow.
Incredible. And this whole setup, it's not just Earth, right?
No, the paper suggests we should expect a similar configuration, generally speaking, for dark plasmaspheres interpenetrating other ordinary planets. In our solar system, exoplanets across the Milky Way.
So the universe might be full of these colossal, unseen dark companions. Wow. Okay, let's zoom in now, closer to home. The actual distribution of dark matter right here around Earth and the Moon, how is it arranged, according to this theory?
Well, first, just to set the stage, scientists generally use the lambda cold dark matter model, lambda CDM, for large-scale.
Right, the standard model.
And it predicts dark matter density increases sharply towards the center of a galaxy. And observations, like from Chandra X-ray Observatory in 2001 and the Sloan Digital Sky Survey in 2003, broadly support that. More dark matter near the cores of galaxy clusters and clumps?
But it's not perfect everywhere, is it?
No, and the paper acknowledges that. There are studies showing subgalactic deviations. On smaller scales, within individual galaxies, the central densities aren't always quite as high as lambda CDM predicts.
So the model needs tweaking at smaller scales.
And maybe some fine-tuning, yeah.
Hmm.
Especially when you factor in interactions with ordinary matter. It's always about refining the picture.
Which brings us to this crucial finding highlighted in the paper, the work of Manoj Kaplinhat.
Ah, yes. Kaplan-Katz's work on self-interacting dark matter, SIDM.
What did he find?
Something really counterintuitive. He showed that the density and distribution of this self-interacting dark matter actually tends to follow the density and distribution of ordinary matter.
Wait, dark matter follows ordinary matter. I thought it was the other way around.
On large scales, yes. But Kaplan found that if a galaxy has a dense center, so does its dark matter halo. If the galaxy has a lower density core, the dark matter forms a hollow or cored region too. The paper quotes his 2018 observation. The CDM model predicts cored, low dark matter density profiles in low surface brightness galaxies and cuspy high density profiles in high surface brightness galaxies. And that agrees best with observations.
So dark matter distribution mirrors ordinary matter distribution, at least for this self-interacting kind.
It seems so. And this correlation, this particle-to-particle density mirroring, it's highly suggestive.
Suggestive of what?
It strongly hints that maybe an attractive force is mediating interactions directly between dark and ordinary matter, which leads to that conjecture of a new fundamental fifth force.
A fifth force, wow.
And the paper adds that self-interacting dark matter is generally found near ordinary matter anyway, because gravity pulls it in. This reduces the distance between dark matter particles, letting their weak electric charge have enough influence to generate structure. It's a subtle interplay.
Okay, so this leads to that fascinating reversal you mentioned.
Exactly, the reversal of cosmic influence. On grand scales, spiral galaxies, etc., dark matter dominates. Its gravity creates the mold for ordinary matter because there's just so much more of it.
Dark matter calls the shots, cosmically.
Right. But at small scales like solar systems, planets, it flips. The higher mass of the denser ordinary matter dominates. So, as the paper puts it beautifully, while dark matter tells ordinary matter what to do at large scales, ordinary matter tells self-interacting dark matter what to do at small scales.
Ordinary matter takes charge locally. That's a profound switch.
It really is a dynamic, two-way conversation between the visible and invisible universe, depending on the scale.
So if we apply that principle directly to Earth's internal structure, what does it predict?
Well, based on that, you'd expect most of the lowest energy dark matter, the stuff with the high mass particles, to be compacted deep below Earth's crust, right where the densest ordinary matter is.
In the core and mantle?
Exactly. It fits perfectly with Kaplan-Katz's observed density correlations. The paper explains that Earth's core, even though it's smaller in volume than the whole planet, will have a much higher particle density of dark matter compared to regions out in the atmosphere or exosphere.
Like how heavy elements sunk to our core when Earth was molten?
Precisely that analogy. Light gases in the atmosphere, heavy elements in the core. Dark matter seems to follow a similar pattern influenced by ordinary matter's density.
But it's not just gravity and this potential fifth force, right? You mentioned plasma dynamics.
Crucial point. Besides gravity and the fifth force, electrodynamics in a plasma environment also plays a significant unique role, especially for the charged dark matter particles. It's a complex mix of forces shaping where everything ends up.
Okay, get ready, folks, because this next bit is truly mind-bending. We're talking about the unseen electric grid, the electrical architecture of these dark systems interpenetrating our planet.
Yeah, this part is fascinating. It starts with the surprising composition of dark matter plasma. Remember how we said it's mostly neutral particles?
Right, 5.5 neutral to 1 charged.
Exactly, about 85% neutral overall, which is the reverse of our ordinary universe, where charged particles dominate elementary neutral ones, maybe 14 to 1. This fundamental difference is key.
Why is it so key electrically?
Because with that incredibly weak, dark electric charge and the sheer abundance of neutral particles, the paper argues that charge separations happen far more readily and are much more widespread in dark sectors than here.
Easier to separate positive and negative dark charges?
Much easier, and they stay separated longer. It's like the system is predisposed to it. The paper describes the whole thing as a colloidal, fluid-like medium. Picture it. Two types of charged particles, positive and negative, just suspended throughout this soup of polarized neutral particles, all under gravity's influence.
A complex, dynamic, unseen mixture.
Exactly. And there's lab evidence that supports this kind of separation.
Lab evidence? Like what?
The paper references G. Tella's experiment from 1996. He studied a two-component plasma in a colloidal fluid under gravity, and he observed something remarkable. The heavy particles consistently sunk to the bottom. The light particles formed a distinct cloud floating above.
Gravity sorting them by weight.
Yep. Gravitational stratification. Numerical models confirmed it. Two heavy sinks, light floats, sometimes forming a separate cloud if the container was tall enough. It's a real physical effect.
Okay, that's one piece. What else?
Then there's H. Thomas and colleagues' plasma crystal experiments from 2002. They generated plasma crystals in the lab, charged particles, neutrals, dust. When they shone a laser on them, the particles didn't just scatter randomly. They spontaneously arranged themselves into as many as 18 distinct planes, perfectly parallel to the electrodes.
18 layers, just self-assembling like that.
Into these neat, flat, disc-shaped clouds.
Like
incredible self-organization emerging from plasma. It really makes that plasma crystal idea tangible.
Wow. So how does this lab stuff connect to the dark Earth?
This is where it gets profound. The paper connects these lab results to a century-old astrophysical principle, the Pannekoek-Rosslund field mechanism from 1922-24.
Pannekoek-Rosslund. Okay, what's that?
It basically says that even a small mass difference between positive and negative charge carriers, like protons and electrons, in a plasma under gravity, can lead to charge separation and generate internal polarizing electric fields.
So gravity pulling harder on heavier positive particles separates them from lighter negative ones.
Essentially, yes. We see this effect in the sun's heliosphere, solar wind, planetary ionospheres. And Alfred's paper argues this same phenomenon happens, but is even more pronounced in Earth's dark plasmaspheres.
More pronounced. Why?
Because of that whole combination we discussed. The weak, dark electric charge, the tons of neutrals, the low density, the different particle temperatures and sizes, all allow for long-lived, persistent charge separation. Gravitational stratification gets amplified.
Okay, so applying this directly to the dark Earth, we get these dark Pannekoek-Rosslund electric fields.
Exactly. And thermal stratification helps too. Those warm, lower-density dark electrons staying separate from the colder, higher-density dark protons. It all pushes towards separation.
Leading to this structure, the dark capacitor analogy.
Yes, it's a great way to visualize it. Picture this setup. First, the E+ region. That's the heavy, positive, relatively cold, more massive dark protons. They sink, accumulate deep below Earth's crust in the core, forming a relatively dense, non-neutral plasma. This is the positive electrode, highest dark matter mass density here.
Okay, positive core, then.
Second, the E region. That's the light, negative, relatively warm, more energetic dark electrons. They hover way out in the atmosphere as a vast spherical shell or cloud around the dark Earth, analogous to our ionosphere, but much, much further out. This is the negative electrode, a non-neutral, low-density plasma cloud.
Negative shell, way out there, and in between.
The dielectric. That's the neutral or pseudo-neutral dark particles. Remember, outnumbering charge 5.5 to 1. They dominate on the surface of the ordinary matter Earth, acting as an electrical insulator between the E+ and E electrodes.
Shielding the positive core, increasing the distance.
Exactly, further reducing the effects of the already weak dark electric field.
And the paper directly compares this to the Tella's experiment.
Yep, provides a table. Heavy particles at bottom, E+ region, light particle cloud above E region, the fluid in between, the neutral buffer zone. It's a striking parallel.
So this whole arrangement basically creates a giant planetary scale capacitor. Positive core, negative outer shell, neutral layer in between, with a dark electric field spanning them.
Precisely. A dark Pannekoek-Rosslund field.
And why is this charge stratification so much more prevalent here than in, say, stars?
Good question. Doesn't really happen inside stars. Fusion, high density, high collision rates just neutralize any separation instantly. Same for brown dwarfs.
And in Earth's rocky core.
Electrons are tightly bound in atoms by the strong ordinary electric force. And neutral particles are atoms whose electrons can be stripped off easily to neutralize charges.
But in the dark plasmasphere,
Particles are much freer, weaker binding forces. So they're highly susceptible to gravity and thermodynamics pulling them apart. This allows that charge stratification to be maintained for really long periods, creating this stable, unseen electrical battery around our planet.
And this isn't just Earth, right? You mentioned the moon.
Exactly. It extends to our neighbor, creating dark moons. The moon also captures dark matter, forms its own dark moons.
With the same structure.
A very similar structure, an M+ region, high positive concentration in the moon's core, and an M region, high negative concentration in a shell hovering above the moon's surface.
And neutrals on the moon's surface.
Predominantly, yes, acting as the dielectric again. And the visible moon co-rotates with its dark moons. They all interact gravitationally, causing tides within each other. It's a whole invisible twin system.
Okay, so we have charged particles, structure, movement, leads naturally to magnetic fields, even dark ones. How do they arise?
Good question. The paper details the generation of dark magnetic fields. As those cold, massive dark protons sink to the core, the E+ region, their collective motion creates a weak current. And that current generates a weak dipole magnetic field. Basic electromagnetism.
Like a seed field from the sinking proton.
Right. Plus, because you have these distinct polarized regions, the core, E+, and the outer shell, E, and moving charges, weak vertical currents naturally develop between them.
Like Earth's atmospheric currents between the surface and ionosphere.
Analogous, yeah. But in dark Earths, the electrodes are much further apart, and there's no rocky core blocking the way completely. These vertical currents generate weak global magnetic fields, and these provide the crucial seed magnetic fields for a dynamo mechanism.
Ah, dark dynamo. What powers it?
It's thought to be powered by the rotation of the dark plasmasphere itself, plus convection. Convection flows of plasma driven by that thermal gradient cold positive core, hot negative cloud.
Rotation and convection stirring the plasma.
Exactly. And as charged particles spiral around these dark magnetic field lines like they do in our magnetosphere, they create dark Birkeland currents, often filamentary currents.
And this dark geomagnetic field, it just sits there.
No, it co-rotates with the dark Earth,
Yeah.
dynamically changing its size and shape along with the plasmasphere. The moon, by the way, would have much weaker dark electric and magnetic fields, being less massive.
Okay, magnetic fields generated by charge movement and rotation. Now, what about the internal architecture? You mentioned those experiments with nested shells.
Yes. H. Thomas's experiments with plasma crystals forming those neat concentric shells, Coulomb balls, that were really stable. The paper suggests dark Earths might have a similar intricate internal structure, nested concentric shells and cells.
How does plasma do that? Self-organize into shells?
It's a fundamental property. Plasma can electrically isolate sections within itself using structures called double layers.
Double layers, like membranes.
Kind of like electrical membranes, yeah. If the voltage difference in a plasma gets big enough, a thin double layer forms. It manages to preserve the overall quasi-neutrality, but the strongest electric fields are found right inside these thin layers.
Okay, so how does that make shells?
Well, in a spherical system like a dark Earth with that positive electrode in the core, E+, and the negative shell electrode around it, E, these double layers would naturally form a series of spherical shells in between.
Like layers of an onion.
Exactly. A series of double layers creates these concentric shells, separating plasma regions with different properties, density, temperature, plasma frequency.
And the number of shells can change.
Yeah, it can vary over time, depending on the voltage potential between the electrodes. And these shells between the E+ and E regions are mostly quasi-neutral, thanks to the double layers and all those neutral particles. The double layers act like dielectrics in a capacitor, insulating, allowing charge polarization and storage.
So the magnetic field, does it influence these shells?
Absolutely crucial role. The double layers don't just form randomly, they follow the contours of the magnetic field lines. The magnetic field provides the unseen skeleton shaping these shells.
Oh, okay.
Dark Birkeland currents run along these fields, and the double layers can even accelerate charged particles. Plus, experiments by Sarma and colleagues showed magnetic fields can induce rotation in these nested shells.
So the field shapes them and spins them.
Yeah.
Wow.
Yeah, it's an active participant. And where adjacent plasma within the shells have different properties, even more double layers can form, separating them into smaller cells.
Cells within shells.
Right, analogous to the granulation patterns on the sun. These cells would have slightly different plasma frequencies, densities, temperatures, creating this incredibly complex, dynamic internal landscape, always reorganizing.
And the shell structure, it might explain things beyond Earth, like in
Yeah.
galaxies.
That's the really grand implication. The paper connects this to observations of elliptical galaxies. Deep images show faint but distinct concentric shells in some of them. like NGC 7600, NGC 3923.
Shell galaxies, they're called.
Yep, about a tenth of ellipticals are classified that way. They have these shells in their galactic halos way out from the main starlight.
What's the usual explanation for those?
The leading idea is a galaxy merger. A big galaxy eats a smaller one, creating gravitational ripples like waves on a pond forming shells of stars.
Makes sense. But Alfred suggests an alternative.
Yes, a fascinating one. He proposes the underlying dark matter halo itself is composed of dark plasma that organizes into concentric shells via these plasma dynamics we've been talking about.
So the dark matter forms shells first.
And then, through gravity, these structured dark shells act as a template, molding the distribution of the ordinary stars, which then visibly show the same shell pattern.
Whoa, that flips the script. Dark plasma structure dictates visible galaxy structure.
That's the implication. A profound shift.
Yeah.
And it suggests Earth's own dark matter halos, the dark Earths, should also organize into concentric shells and show other plasma features, filaments, vortexes, plasmoids.
Okay, let's bring this amazing, sprawling theory back home again. We've covered structure, dynamics, plasma physics. Now, let's try to map it. How much dark matter is actually thought to be around Earth and Moon, and where is it?
Right, pinning down the numbers. Well, starting broad, calculations by Yu and Siegel back in 2008 suggested that within Earth's orbital radius, dark matter density is significantly boosted
How much?
by more than 4 orders of magnitude over the local background halo density. They estimated a total mass of about 3.3 by 1016 kilograms of that region.
That's a lot of kilograms.
It is. And then the implication is that all planets might have these dark matter counterparts, gravitationally bound, co-rotating, a universe richer than we see.
Which leads to that early estimate, the Adler line.
Ah, yes. Stephen Adler's 2009 hypothesis. Really clever idea. He thought if the combined gravity of Earth and Moon seems stronger than their individual masses would suggest, maybe that difference is a dark matter halo between them.
How could he measure that tiny difference?
Using the Lagios method. Precise laser ranging. Bouncing lasers off the mirrors left on the Moon by Apollo and off the Lagios Earth satellites. If Earth pulled harder on the distant Moon, relative to its mass, than on the closer Lagios satellites, it could signal a dark matter halo in between.
Did it work? What did he find?
Based on this method, Adler estimated about 24 trillion metric tons. That's 2.39 by 1,016 kilograms. Very close to the Yu and Siegel number of dark matter lies in that space between Earth and Moon.
24 trillion tons. Wow.
Yeah, and he even speculated this halo might explain the anomalies seen in the orbits of spacecraft like Pioneer, Galileo, Cassini, those weird unexplained accelerations.
That's been a puzzle for ages.
It has. And Adler estimated this dark matter density peaked around 70,000 kilometers, about 44,000 miles from Earth's center, forming a vast spherical shell or cloud.
And that distance is the Adler line.
That's the informal name, yeah. A fascinating contrast to our Kármán line at just 100 kilometers to the atmosphere. Now, while 70,000 kilometers is relatively dense for a cloud, it's still considered lower density than the dark matter expected in the core, or right on the surface.
Okay, so a peak density way out there. But what about closer in, like right here on the surface?
More recent studies have looked at that. Rebecca Lean's 2023 work is really intriguing. Her team included factors like thermal diffusion, gravity, capture accumulation for neutral dark matter for the first time.
And their conclusion?
Quite surprising. They found it's possible to have a high concentration of neutral dark matter particles floating right on Earth's surface, significantly displaced from the core.
Floating on the surface, how dense?
Potentially exceeding the local halo density by 10 to 15 orders of magnitude. Astounding density. This assumes asymmetric dark matter, where the lowest energy neutrals cool down and reach thermal equilibrium with us. So, yeah, maybe an incredibly dense, unseen layer right under our feet.
Unbelievable. Okay, surface. What about deep inside, in the core?
Recent analyses from 2023 for the IceCube neutrino detector and the Super K experiment have put limits on that.
What kind of limits?
Well, IceCube ruled out dark matter being more than 32% of the core's mass, or 24% of Earth's total mass. Super K ruled out more than 21% of Earth's total mass. Combining these, the overall estimate is roughly 20% of the entire planet's mass, and maybe 30% of the core's mass could be dark matter.
20 to 30%. That's a huge unseen component of our planet.
It really is.
Okay. So let's put it all together now. Synthesize these findings. Paint that picture of the topography of dark matter in the lowest energy dark Earth-Moon system. This is the aha moment, connecting all the pieces. First, the mass and number density overview. Where is it densest?
Okay. Dark plasma density peaks in Earth's core. That's the E+ region, mostly positive particles, concentrated in that smaller volume.
Then.
Medium to high density right on Earth's ordinary surface, dominated by neutral particles but mixed with smaller, equal numbers of positive and negative charged ones.
And further out.
A low-density cloud, that vast spherical shell of negative particles around Earth, the E region, spread out over a much wider volume.
But overall charge balance.
Roughly, yeah.
Mm.
Total positive and negative charged particles are thought to be about the same, preserving overall quasi-neutrality.
Okay, now that fascinating pattern, the charge density wave as you move outwards from Earth, walk us through that again.
Right. Imagine starting at Earth's center and moving out. You begin with high positive charge density in the core, E+, slowly decreasing towards the surface.
Okay.
Then, high neutral charge density on the visible surface, dominated by neutrals with that equal mix of positive and negative charges.
Got it.
Journeying further out, you hit a peak in negative charge density at the Adler line, around 70,000 kilometers out. That's the E region.
The main negative shell.
Yep. Then, continuing towards the moon, there's a slight increase again in negative charge density nearer the moon, maybe 12,000 kilometers from its center. That's the M region, the moon's negative shell, estimated.
Okay, second negative peak near the moon.
Then, neutral charge density increases again as you approach the moon's physical surface.
More neutrals on the moon's surface.
And finally, positive charge density increases again to peak inside the moon's core, the M+ region.
Positive core in the moon, too. So it's like positive core, neutral surface, negative shell, then repeat for the moon, roughly.
That's a good summary, yeah. And the vast space between the E and M regions, that's described as a dark collisionless plasma, mostly neutral dark matter, with smaller, equal pools of dark electrons and protons floating around, a very neutral sea.
And you mentioned a bridge, a dark bridge.
Yeah, intriguing idea. The paper suggests that at perigee, when the moon is closest to Earth, their gravity might pull strong enough to form a tenuous dark bridge, connecting the lowest energy dark Earth to the lowest energy dark moon.
Like an invisible tendril reaching out.
Exactly. Paints a picture of this dynamic, interconnected network, sometimes literally touching.
Okay, finally, put the scale of this lowest energy dark Earth into perspective one more time. It's hard to grasp.
It really is. The paper references a table comparing radii. Ordinary Earth, mean radius 6,371 kilometers. This lowest energy dark Earth, mean radius 70,000 kilometers.
10 times bigger radius.
More than 10 times. Its volume is enormous. 1.44 by 130 cubic centimeters compared to Earth's 1.08 by 127. The analogy might be like Jupiter's gas envelope, about 71,000 kilometer radius surrounding a solid core roughly Earth size.
Okay. And the truly mind-boggling fact.
This dark Earth, with the Adler line as its fuzzy border, it could fit more than 1,000 visible ordinary matter Earths inside itself.
1,000 Earths inside this invisible structure interwoven with ours. That's humbling.
And awe-inspiring.
It absolutely is. Changes how you think about our place, doesn't it?
Completely. Wow, what an incredible, profound deep dive we've taken. We've journeyed through this unseen, complex, dynamic world of Earth's theorized dark plasmaspheres, from, why dark matter forms plasma in the first place, to their nested structures, their potential influence on our planet, even potentially explaining cosmic mysteries like those shells in elliptical galaxies. It really is a reminder that the universe holds so much more than meets the eye.
Definitely. So can you synthesize the key takeaways for everyone listening? What are the absolute must-remember points?
Okay, sure. I think the big takeaways are, first, dark matter particles aren't just in a uniform cloud. They seem to be trapped in distinct structured regions. Earth's and Moon's cores, surprisingly on their surfaces and in the space between.
Not just diffuse, but localized and structured.
Right. Second, each body, Earth and Moon, has this layered structure. A dense, dark core, a much less dense spherical shell or cloud surrounding it way out, and a fairly dense layer right on its surface.
Core, surface layer, outer shell.
Exactly. Third, these densities generally track ordinary matter densities, but they're also heavily shaped by unique dark plasma dynamics, like that charge separation.
Plasma physics is key.
Absolutely. Fourth, these dark Earths are essentially dark matter planets, gravitationally bound, co-rotating with us. They have their own weaker but maybe more pervasive dark electric and magnetic fields, unseen companion planets. And finally, each larger, higher energy dark Earth encompasses and interpenetrates the smaller, lower energy ones, organized into those intricate concentric shells.
Nested structures getting bigger as you go out.
That's the picture the paper paints.
Okay, so what does all this mean for you listening right now?
Well, maybe the most profound, the most thought-provoking idea from this whole deep dive is the author's suggestion near the end, that some of these incredible dark plasma shells might even be capable of harboring a dark biosphere, one that supports dark plasma life forms.
That's the truly paradigm-shifting idea, isn't it?
It completely redefines what's possible, expands our whole understanding of what life could be, suggests the universe, right here in our own cosmic backyard, is potentially far more vibrant, complex, and teeming with unseen possibilities than we ever dared to imagine.
Makes you look at the space around us very differently. It certainly does. Well, that's all the time we have for this deep dive. Until next time, keep looking up and keep exploring the hidden dimensions of our universe.